So these are the notes from the first part of chapter 11, which is going to talk about work and potential energy and the relationship between the two. So we're going to focus the first part here on the work. And so work and energy are very closely related. So work is just force times distance. Force in newtons, distance in meters, we get a unit of a newton times a meter or a joule. And a couple of rules. You have to move something in order to do work, clearly because distance can't be zero. And the force and distance have to be in the same plane. Like they have to both be vertical or both horizontal or both at an angle or no work is done. And you get positive work if you move, if the force is applied in the same direction as the object is moving. You get negative work if the force is applied in the opposite direction. So this would be an example of something, if you wanted to slow something down. It was moving at you, applied a force opposite, you'd have negative work, but that would stop the object. So here are just some scenarios. Is work being done? If I push on a goalpost for an hour, it's not going to move. Distance is 0, therefore the work is 0. I carry the football down the field for a touchdown. This one's a little tricky. This one just assumes that I'm kind of dumb and just holding the ball barely so that it just stays off the ground. And if I do that, the force that I'm applying, or the distance I'm going is horizontal, but the force that's being applied to the ball is vertical. And so horizontal and vertical are not in the same direction, so this would be no work. I fumble the football, work is done because the force is down and the distance is down. I recover the fumble, the force is vertical, the distance is vertical. I throw the football for a touchdown, distance is horizontal, force is horizontal, and I mow the football field. Now if I'm using like a push mower, I'm applying the force at an angle, and I am moving horizontally. But part of that force is horizontal. And so yes, I do work. So if you're at an angle, you need to find the component of the force. And typically that's going to be the cosine. So for example, if I have a force that's this way, but the object is moving in this direction, so this is the D, this is the F, then I'd have to find this component here of this angle, and this would just be F cosine from our components. And so then I would take this times this to get the work, because this is these two match, they're in the same direction. All right, so here's a clicker question. Which force does the most work? Here, I need a pointer. So force is vertical, distance is horizontal. This would be 0 work. Here in this example, they're in the same direction. Here they're not. I would need the horizontal component, and that would be 8 newtons times the cosine of 60, which is 4 newtons, would be this way. So 6 newtons does the biggest amount of work. So here is an example. A rope inclined at 45 degrees, and the tension in the rope is 20 newtons. 45 degrees here. How much work does the tension do if the suitcase is pulled? So there's the distance equals 100 meters. And so here I need to use the force, 20 newtons, times the cosine of 45 is 14.14 newtons, and so the work is going to be 14.14 times 100. And again, it's because this force here, which is the 14.4, is in the same direction as the displacement. And so this is going to be 1414 joules. So work is needed to change the energy of an object. We call that the work energy theorem. Both energy and work are measured in joules. And so this is just a different way of writing that same statement, that the work is equal to the change in energy. And the energy could be potential or it could be kinetic. And so these are just the specific versions. So there's the work equation, and then the change in kinetic energy would be the 1/2 mv final squared minus 1/2 mv initial squared. If you're talking about gravitational potential, again, there's the work, mg height final minus mg height initial. And then if you had spring elastic potential energy, again, there's the work, 1/2 kx final squared minus 1/2 kx initial squared. Typically, one of these final or initial conditions that you see here on the right-hand side is 0. So you often end up with just this FD equaling either 1/2 mv squared if you're turning your work into kinetic energy, FD equals mgh if you're turning it into gravitational potential, or FD equals 1/2 kx squared if you're turning it into elastic potential. So here is an example. We've got applying a force up the ramp, moving the ball 1.5 meters, and it gains 30 joules of potential energy going up the ramp. What force must the mechanism exert on the ball? And so here we have to do work, so we have FD, but we're turning that work into gravitational potential energy. And so it actually tells us it gains 30 joules of potential energy. So if I'm looking for just the force, I would take the 30 divided by the distance I have to apply the force. So it has to be this distance here because I'm applying the force up the ramp. So this would be divided by 1.5, and I would get 20 newtons. So here the kinetic energy of a particular car traveling at various speeds is given in the table. Which of the following requires the largest amount of work from the brakes of the car? So work would be the change in kinetic energy. And so if you look, if I go from 40 to 30, I need 70,000 joules of energy. From 30 to 20, I need 50,000. From 20 to 10, I only need 30,000, and from 10 to a stop, I'd only need 10. So clearly going from 40 to 30, my brakes would have to do the most work. Here's one: a car traveling at 10 miles per hour slams on its brake and skids to a stop after traveling 8 feet. So 10 miles per hour, 8 feet is how much distance I need. Assume the frictional force acting in the car is the same. How far will it skid before stopping if it locks its wheels going 30 miles per hour? So this is that looking at FD equals the work done by the brakes is changing the kinetic energy of the car. It's stopping it. So essentially I'm looking at the distance and how it's related to the velocity, because we're keeping everything else the same. So if looking at what I did to the velocity going from 10 to 30, I tripled my velocity. 3 squared is 9, which means the distance has to be 9 times greater than what I had before. So 9 times 8 is going to give me 72 feet. And again, this is one of those great what-if questions. Okay. And then we have an example with Mr. Incredible here. He stops a moving train that was moving at 50 miles per hour in a distance of 100 meters. What force did he apply? First thing we have to do is actually change the miles per hour to meters per second. So 1 mile, 1610 meters, and 1 hour, 3,600 seconds, gives me 22.4 meters per second. And then we're going to stop it. So this is one of those where you have FD equals 1/2 mv squared, and I'm looking for the force. So I'm just going to divide both sides by d. So the F in the end, I'm going to have 1/2. Mass is 20,000. And then I'm going to have my 22.4 squared. And then all divided by the distance of 100 meters. And if I run and calculate all those numbers, I get just about 50,000 newtons. And so he is Mr. Incredible. All right, and then the last section that we're going to look at here, it has to do with the work done by a variable force. So the force isn't always constant. So if the force changes, then we have to be thinking about an integral. And remember, an integral just means we're talking about an area under a force versus distance or force versus position graph. And then that will give us the work, which will give us the change in energy. And so here is an example. Particle moving along the x-axis experiences the force shown in the graph. If the particle has 2 joules of kinetic energy as it passes x equals 0, what's its kinetic energy when it reaches 4 meters? So in order to find the change in kinetic energy, I need this area. So delta K is going to equal the area, which is going to be 1/2 the base, which is 4, times the height, which is 2. And the 2's cancel, and so I end up with 4 joules is the change in kinetic energy. This is a positive change, so the Kf would equal 2 plus the positive change of 4 gives me 6 joules. And then the last slide that we have here has to do with, we've got a car. What's the car's speed after traveling 200 meters? So again, we can find the work done by finding this area. So 1/2, the base is 200, the height is 10,000, and we get 1 million. Now we just have to set that work equals the kinetic energy, and if we rearrange for V, it's going to be the square root of twice the work divided by the mass. So 2 million divided by 1,500, and then take the square root, and I get about 38 meters per second. And since it started from rest, then that will be its speed. And that's the end of that part.